All right, it is 12 o'clock. Good afternoon and welcome to the Center for STEM Education. This is the first speaker in our Spring 2020 speaker series. I'm very excited to introduce Dr. David Utal. David and I have known each other for lots of years, and he does all kinds of really cool interdisciplinary things, and I'm just so excited he's here today. David is a professor of psychology and education at Northwestern University. He leads a research laboratory of undergraduate, graduate students, and postdocs engaged in a wide range of experimental and observational studies focused on cognitive development. His current interests include maps, symbolic representation, informal learning, and spatial thinking in STEM education. He's also particularly interested in spatial thinking in STEM education. He collaborates with researchers and practitioners at Chicago's Children's Museum and the Spatial Intelligence and Learning Center, where he also serves as director. His research is conducted on the Northwestern Evanston campus, in schools across the Chicago area, at the Children's Museum in Chicago, and in collaboration with colleagues across the United States. So thank you, David, so much for being here, and thank you all for participating. This is typically a fairly relaxed and casual atmosphere. If you'd like to put questions in the chat or make conversation in the chat, please feel free. David has a wonderful talk prepared for us, and I'm sure he'll answer any questions at the end.
Yes, and some of you saw about half of it in November. Sorry about the computer failing. I'm pretty sure that won't happen again. All right.
Well, not good.
Yes. Okay, here we go. No, it didn't even advance the slide. Okay. So I'll be talking about two things that are related, but may not seem related at first. The first is, why does spatial thinking matter for STEM? So I think, to paraphrase Kelly Mix said, the relationship between spatial ability and mathematics is now demonstrated to be so strong that it doesn't make sense to ask if it exists. And there's been several meta-analyses that have come out now that control appropriately for other factors that might have. So I actually now firmly believe it. But the question is why? Because that's just a correlation. So that's what I'll be talking about, is why. And then also I'll talk about my own research on learning from maps as a prototypical example of why spatial thinking matters for STEM. Okay. So first,
David, excuse me. I'm sorry. I'm going to stop you for a sec. We've got two rectangles and boxes over your screen. Just makes it a little hard to see.
Okay. Let me just, okay. But if I pull out everything, oh, not again. Okay.
Then just leave it. They're just small. I just thought if you could move your mouse, but that's okay. Keep going.
I think I know what's causing that, but it would take a fair amount to fix. Okay.
And skip, we're good.
Okay. So by spatial thinking, I mean reasoning, representing in your mind, and the transformation of information about locations in space and the relations amongst those locations. And the relation amongst those locations is what I think is particularly important for scientific discovery and reasoning. Okay, so some famous examples from the history of science anecdotally describe this importance of spatial reasoning in scientific discovery. The first is Kekulé's discovery of the structure of the benzene molecule, foundational to organic chemistry, and working in the lab and doing various experiments and compounds, he had figured out what the sort of the elements of this compound were, but he had not figured out the spatial structure, which was, in organic chemistry is often critically important. And so it's not enough to know what the elements are that make up this compound. You have to know, in many cases, how they are arranged to understand what happens in different reactions and make predictions and things like that. So this is probably apocryphal, but allegedly he was on a train, he fell asleep, and he dreamed of a snake biting his tail. And I never understood how you got from the circle to the six-sided hexagonal structure, but it was the insight into the ring, and from there he figured out the six-sided structure. Another example from the history of science is Watson and Crick's. Let's not also forget Rosalind Franklin's important contribution as well. She couldn't share in the Nobel Prize because she unfortunately died very young, but she contributed very much to the basic data that allowed them to make these discoveries. So when this was again an issue of structure, and it was a complex structure for that time. And they have all these properties of what it does, and then they have to infer from that what must be the spatial properties that connect these 4 amino acids and things like that. And in the publication, it's interesting that we wish to put forward a radically new structure for the DNA molecule. So it really shows this sort of radically new. So at least in the history of science, we know that spatial insights have been important. But of course, as a psychologist, these anecdotes are interesting, but not sufficient to actually, to do educational interventions. You wouldn't want to spend millions of dollars changing things for 2 anecdotes. But fortunately now, in the past 10 to 15 years, quite a bit of evidence has accumulated. And the convergence of all that evidence, I now think, is very strong. Any one study is a little, has weaknesses, but together I think they do strongly indicate that spatial ability is correlated with STEM achievement. Now, it's funny to have people who interested in spatial cognition sit around and try to interpret this graph. It's supposed to represent 3 dimensions. The first 2 are easy, math and verbal, 0-centered, so that the average score would be 0, not whatever it is, 600 or whatever. This is scaled, so the average is. Now, the hard part is these vectors, these arrows coming out. And this ability to imagine things coming out in space towards you or away from you is classic in the organic chemistry thing, and it's also relevant here. So the length of the arrows represents the unique contribution of spatial ability to predicting these outcomes. This is a very large longitudinal study that began in 1960 with 100,000 high school students. To the extent that the folks are still alive and can be found, they're still studying them. And so this is now in 1983 approximately, they looked and see who went into these different STEM fields. And you can see the arrows are pretty long. And so that this means that spatial ability is particularly important in predicting, I'm trying to avoid the word determining, but in predicting who went into engineering, for example, with scores that are quite substantially higher than the average. And so you could say, in engineering at least, that spatial ability was more important than mathematics ability. Now, we could talk at some length about why these are negative, but remember, this is prediction. It's not saying these people are dumb or anything. It's just saying their cluster or tilt of abilities push them more towards these other fields. Okay. Medicine may well have changed. I know that biology has changed to become a much more sort of molecular science. So it would be interesting. This is old data. Okay, so but we know that spatial ability, it feels important. Geologists in particular strongly believe, and actually now we know, it's not just that they have high spatial ability, it's that it's sort of part of their everyday practice and knowledge. So a structural geologist, I've been told, is like, the job is to unfold a car wreck that occurred over 100 million years or something. But you can definitely see if syncline, anticline, I don't know, I can't remember which is which, but you can definitely see there are spatial forces that created this pattern that you observe. And so sort of undoing that in your head, unrolling that snowball is, challenging. Moreover, we now know that the standard tests of spatial ability are not enough to describe geological practice. For example, when we talk about rotating chemistry molecules, for example, at least what I'll show you, the molecules don't break apart in the rotation. But geologists have to think of non-Euclidean shearing and things like that that affect things in one dimension but not the other. So and they think a lot about whether a transformation will break the rock or not. So those are not things that psychologists have studied until the last few years, and that sort of shows the value of this interdisciplinary collaboration, which I hope to continue. It's not just me trying to help you. I think that's, patronizing, but what is instead is we learn a great deal as well. Our theories and our tests were inadequate to cover what was really fundamentally important in geology. Things break and fold in ways that are not well predicted by your standard Euclidean rotation. Okay, it's also very, very important in organic chemistry. Handedness or chirality is just a fundamentally spatial concept that matters a lot in understanding what molecules are and how they behave. And this difference can make an enormous effect. And like the famous thalidomide case was a failure to distinguish between two antimers which shared the same chemical properties but not the same structure, right hand, left hand. So these things are important, and we also know they give students a lot of trouble. So this joke may be getting old, but let's see. The best source of psychology majors is the organic chemistry course. In that I've counted now 7 people, this is over a long career, come to my door in the psychology building and say something like the following: I thought I wanted to go into medicine, but organic chemistry has convinced me that I don't want to go into science, therefore I want to be a psychologist. Now that hurts because we like to think that we're a science too, but the general point is well taken. And a lot of them, when you interview them in sort of a qualitative way, many of them do refer. The professor was saying, can you see this 3-dimensional structure coming out of the chalkboard, or just saying it, that look at this. The professor has been doing this, for 20, 30 years, and it is immediate and does not seem difficult. But for the novice, it may be very, very difficult. And there are ways to make it easier. So we could probably, whether it's organic chemistry wants to be a weed out course or not but I think as we're thinking about ways to be more diverse in terms of the students that we serve, the idea of weed out courses might be something we want to reconsider, and the relevance of spatial skills in early organic chemistry is important. It's also interesting to note that by the time you get into the later part of the second semester, it's a lot of mathematical things, and they have to understand the spatial stuff to get the basic concepts, but then a lot of the solutions that they do are not using that. So that's another interesting problem. Okay. So, but the question is why? As I've said, these are just correlations. And there's lots of reasons why. And I'm going to ask us to think about one general reason, which is that spatial cognition strongly supports relational thinking. And so I have to explain more about what I mean by relational thinking. So it's a key characteristic of human thought. And some have argued it is what differentiates us from other species. Now, I risk being specious, and I don't mean, I know every day we discover that crows and dogs are really, really smart, and my dog is very smart, and I accept that, but there are some things that non-human primates, for example, our closest relatives evolutionarily, have a lot of trouble with, that you can't stop a 4 or 5-year-old child from doing. So I'm not saying it's all or none, but I am saying there's a big difference of kind. There are studies that have gotten relational thinking in crows and members of that family, as well as in some apes, but I would hate to be the research assistant doing that. I mean, you're sitting there reinforcing these crows, like over 10,000 trials. And it's, like I said, you can't stop a human child from doing it. So STEM is often about relations and patterns, okay? And now we're talking about relations and patterns in 3 dimensions. So geology is both time and space, and time at a scale that most students are not used to thinking about. And students tend to do well when they are able to think relationally, and spatial awareness facilitates doing so. So what I mean here is thinking about information of terms of connections between items. So this is what a very simple example that's something that kids can do pretty easily, that many of these intelligent species of animals seem to have trouble with. This is called a relational match to sample task. And it seems very simple. Which of these two is like the top one? Now, what makes this interesting and relational is it's about a pattern of two-ness. The individual identity doesn't matter at all. And in fact, it gets in the way. So if you start thinking about stars and triangles and circles and squares, you may be going down a garden path that is going to make it harder for you to solve. So but like I said, by about age 4 or 5, it just, the kids can see it and do it. So like I said, despite all we know about the COVID, is it family? I know, and like I said, chimpanzees and now dogs do seem to have inference into human social cognition, but this isn't social cognition. But like I said, the 4 or 5-year-old child has no trouble. Okay, so relational thinking is not only spatial thinking, but when we spatialize information, we often make it easier to think about relations. So this cladogram, very common in evolutionary biology, it doesn't really, I don't want to misspeak, but showing evolutionary relations amongst different species. So, discover your inner fish, because we all come from fish eventually. So this is not really spatial information when you think about it. There's nothing really that spatial about it, but we're so used to representing it that way that it's almost hard to think about it without the representation. I mean, just to show you, in the history of microeconomics, like I think Adam Smith is like 1780 something. That book does not have any charts, but it's hard to imagine economics without charts now. And the point is that it's not inherently, supply and demand are not inherently spatial. But when we look at the intersection of supply and demand curves, we immediately see price. And that's the same thing here. We see relationships. Okay. Now I want to go a level deeper in talking about why it matters, and it has to do with how people process analogical information. Analogies are about relation. Analogies are fundamentally important in the history of science, and they're greatly aided by spatial representation. Here is one famous analogy between the structure of the atom and the solar system. The solar system, we shouldn't, by the time I think it's Maxwell is working on this is already known, but don't forget, people lost their heads and stuff for even suggesting this. So this was no easy discovery either. But by the time that we worked on the structure of the atom, we knew about orbits. And what makes this analogy so important is the relational nature. It's about something in the center and multiple things, be they electrons or planets, revolving around that nucleus or star. Okay, that is the thing in a predictable way. Now, whether this, I know that there are orbitals, and this is actually it's not this simple. I know that, but nevertheless, the idea of orbits definitely applies to orbitals. So now this is a very relational thing. Now to get a sense of what I mean by that, what if a student, maybe a 3rd grader, 4th grader, is struggling to understand this, and you're the teacher and you want to help them, and you say, student, let me help you. Look, both the sun is yellow and this part of the nucleus is yellow. That doesn't help. In fact, it gets in the way, because that's an object relation. That is leading you down the wrong path. What you want to focus on is relations. And so what makes relations matter is so critically important to scientific discovery. This is not just spatial. It's putting space and time together that led to the great insights of sort of the foundation of modern geology, was the combination of the patterns of paleontology and geological history that together they converge on this conclusion. Either one in isolation makes it hard, but when they converge like this, an explanation pops out. Periodic table is another really good thing. We learn about the structure and how they're related to each other. We can make predictions about elements that have not yet been discovered. They fit neatly into predictable patterns. If you really think about it, this information isn't spatial either. Atomic number and all that, you can describe it. But we have the strong desire to spatialize it. It's almost impossible now to talk about relations between elements without spatializing it. Okay. Sorry, I did the admission there. Okay, so now I want to talk about my colleague Dedry Gentner's theory of analogy as structure mapping. Okay, and remember this idea I brought up in the planet and the atom between orbits, that's the relational information, and object information, which is like the color of the sun. Sun's not yellow anyway. So as I've implied, analogy can be understood at two levels, and we really need both. But what makes analogies so powerful is usually the relational information. So I've already given you an example. This is a little bit different, but this is about solving relational information. In this case, it's about middleness, and middle is different than the two not in the middle. Okay, middle is an inherently relational concept. I could measure the big square from the two sides, so say that like 4 millimeters, maybe a little bit more, but that doesn't give you any good at all. In fact, it probably is bad. I could tell you that this circle is filled with this sort of light blue, but that doesn't help you at all, other than the fact that it's shaded. And so if I start going into the actual color of shading, which is a strong object property, I'm leading you down the wrong path. Now, I'm hoping you see the relation between this and orbits. They're both relational patterns. Now, you do need objects. Like a student who's struggling with this may need the support of mapping out the individual items. But if you stop there, and it's kind of a tension, a good teacher knows when to emphasize objects and when to back off and let the child discover the relational pattern. This is, in music, learning music, in any instrument, you practice relational patterns over and over and over and over again. Scales are but one example, so that you can transfer this pattern of relations to a new context. At least that's the theory. Okay, there's the answer. Okay, now, just to sort of indicate what I mean, Raven's progressive matrix is, some people have called it a culture-free intelligence test. That's pretty strong because, cultures vary in access to materials like this. So I don't want to go that far, but it's a lot better than, say, vocabulary. And what makes this interesting is this test is more correlated with all other IQ tests than any other test. So like if you wanted to say what test best captures overall intelligence, it would be this one. And notice that, in fact, there's a recent computer modeling thing that strongly suggests people solve this through a relational pattern, trying to figure out what's similar, what's different. This is much harder, and I'm just going to go on because I'm sure I get the answer wrong, but you're trying to think about patterns and relations. Now, just to sort of, this is kind of the exception that proves the rule, kind of. So what Markman and Gentner did in this study is reverse the objects, but maintain the relationship. And people really have no trouble, adults have no trouble transferring this, but a young child might, because they're going to say, oh, it's a Volkswagen, or I have a boat, or something like that. So this one is this is what we call a cross mapping. And it's a little bit, at risk pedagogically, in that it's very easy to focus on Volkswagenness and not on, which is an object property, and not on the pulling relationship. But you can see how the fact that we can solve this sort of just highlights how different objects and relations are. This is what we call an alignable difference, because it's alignable in that they share the same relational structure. If I asked you what's different about these, that would be very, very easy for you to solve, because what you care about is the relation. Likewise, if I say, what's the difference between a fork and a car? That's a crazy question. But if I ask you what's the difference between a motel and a hotel, most people immediately start listing all kinds of differences. Like you can pull your car up in the motel, but in the hotel, you have to walk through the hallways. There's often elevators in hotels. There may or may not be elevators in motels. But if you think about it, motel and hotel are actually very similar, and car and fork, or whatever I said, are very, very different. So it should be, I mean, there are more differences between fork, but the fact that we align these like this makes the differences just fall out, if you will. This is why before and after photographs are so powerful. People are obsessed with these. There's something on Facebook going around, post yourself 10 years ago, and now it's going all the way back to 40 years ago. Not everybody can do that. Most people on Facebook can do 10 years ago. And we find these so inspiring because it captures both the objects and the relations, and we powerfully notice the object differences. This is an object difference. We align, and then we see immediately that the belly is much smaller on the right. And likewise, these kinds of things. This is actually about 5 miles from the house of Mary Haggerty, a fellow spatial really. One of the many California disasters. You see, I mean, it just drives it home so dramatically. And the reason is because the relational structure is the same, but the objects now have changed. But the relational structure has to come first. And we can do this in anatomy learning. So a bird and a human might not seem that similar, certainly on the exterior, but it's useful for students in learning the anatomy to compare and contrast the similarities. There is a similarity of structure. They're both chordates. They both have a backbone, and that matters. And then there's the patterns of attachments. It's far from the same. You can learn a lot by comparing, for example, a bat's wing and a bird's wing. About you realize that the bat's wing and our fingers and hands are not as different as they might seem. That's, again, first relations, then objects. And comparing things promotes relational thinking. It is the way we get abstraction, how we are able to think about things like orbits and orbitals is because we studied and compared multiple examples. This, in theory, makes the knowledge more portable. If we're lucky, it applies to new situations. Now, of course, this is hard. A lot of students will take a very hard class, do well, and then when the same material is presented in a slightly different context, it may be very hard for them to apply it. But I think we can teach it in a way that at least it's more likely. And then another thing to do is give a hint, because context matters and people tend to lock things into context. But if you say something you learned in the past here is relevant and give an example, it may be easier. Okay, so amongst the many cool things that Dedry has said, space is the universal donor of relational thinking, or Tom Lowry, space is a vehicle for thinking about STEM concepts. And I think most STEM concepts we care about are relational. So space makes it much easier to think about relations. And that has to do with the structure of the visual system and the brain. So we can depict information. We see relations. It is as if we are looking at the relations. Now, it's not so simple as that we record a mental image, but by pulling in our visual system, we're able to see patterns and relations that we couldn't otherwise. Most of us are very linguistic creatures, but language is not good for keeping track of relations because you have to remember each individual object. In fact, if I ask you, for example, where is Houston in relation to Jacksonville, Seattle, New York? You're very tempted, as I add more and more cities, to draw a map because it makes the relations comprehensible. Okay, so space is a universal donor for scientific thinking, math and logic, and ordinary conversation. Are you following my line of thinking? So the line idea is relational in that everything converges and it goes into space. Okay, it also seems to be very important in young children's learning. Now, this is new research. It's not mine. I wish it was, but it's by Bethany Riddle Johnson at Vanderbilt. And she's been studying the role of patterning in children's early mathematics. Now, I remember a quote, I don't know where I heard it. I wish I could attribute it properly. Every good kindergarten teacher knows the value of patterning. And for some reason, I can't fully, kids love these kind of things. This isn't a hard one, but it is a relational pattern. We can describe it as A, B, A, B. It's not really about ducks. We can almost immediately perceive that this pattern, the top one, ducks and stars, is different than the next one, which is AAB, AAB, ABA, and so on. And this is obviously really important in music and lots of things where we look for recurring patterns. And that is a form of relational processing. Bethany has shown that patterning at age 5 predicts math score in grade 2, and it may be because you're helping the child understand the importance of relational structure. This is very speculative. I don't think we really know, but I'm convinced by the evidence that it matters. Another example from Liz Gunderson's research is the importance of the number line in learning about the properties of number. People are not born with the concept of integer. Now, we are born with some things about number, but they're only precise up to like 4 or 5. After that, it's a long slog, about 4 years to learn this. So a child at age 3 or 4 who can count to 10, it may be impressive, and it will be part of their learning. But that in no way means that they understand that 7 is 1 more than 6, and 8 is 1 more than 7, and that there's a progression, and the order that you're doing in these things is for a reason. And it seems like learning the number line is a critical part of it. The number line is about as relational as you can get, one number after another, same distance apart. It seems like children's sort of innate estimates of large numbers are logarithmic. There's more or less, but getting the these precise integer linear scale happens somewhere between about age 6 and 8, and it's that could be contributing to the previous thing on patterning. So number lines matter, and representations like this matter. So the first thing that's really hard is this number sense of understanding how numbers spoken and numerals map on to quantities. You can have weird things where children will say, there's 2 dogs, and you add another dog, and they say, look, there's 5 dogs. And it's just not so simple. As adults, it seems very, very natural, but it's not. Okay. And if you think about it in sort of learning mathematics, there are some very well-known roadblocks starting in preschool and going all the way up to pre-college or early college. And all of these have to do with relations. Number sense is about relation between integers, and fractions, is relational. Algebra is functions, not individual numbers. So a function describes a pattern or a relation in a mathematical sense. And then ultimately calculus is relations amongst functions. If you ever sit on a grant panel for education that has anything to do with mathematics, you will see these three, the first three, mentioned as like, if you don't get number sense, America is failing, and it's always the same introductory paragraph. The only thing that differs is whether they say number sense, fraction, or algebra, depending on what age they're focusing on. Fundamental theorem of calculus is really about understanding, taking things apart and putting them back together again. Integrals and derivatives are the opposite of each other. That's very relational. So instructional implications are that we should use spatial representations to help students think about relations. But the design and implementation of these spatial representations is not so simple. So people often think, well, if I can draw a picture's worth 1,000 words. So if I just draw a picture, the students will understand it. Sometimes yes, sometimes no. It depends upon what you're representing. And I'm hoping that this talk gives some initial insights into how we might go about representing things visually in ways that comprehend. So if you're teaching organic chemistry, the Fisher diagram, there's like 3 different ways that they represent the third dimension. And this goes back before the last century. And everybody had to learn it, but they're not obvious. And it may take some time, and using multiple representations like blocks and models to get it down. So this is an example of what I mean. Now, this graph seems very, very easy to understand, but I would argue that this is not really what we need a graph for, and that by doing it this way, we are actually focusing on object properties. So it's very, very common when you start teaching children graphs to have them count out something. So you might show them model police cars and ambulances, or this problem is represented in countless different ways across somewhere between kindergarten and 3rd grade, depending on what your teacher believes, what state you're in, and things like that. Anyway, so the child learns that, there's 6, and look, it goes up higher. Didn't you just say it's like a number line? Okay, but what this is doing, in my opinion, is taking, there's no pattern here that I can discover at all. And maybe that's fine in the beginning, but what we want to use the graph for is to think about relations and patterns. So, a lot of these prompts or scaffolds must sow the seeds of their own destruction, if you will, because if you just focus on objects, then it's going to be really hard to use. I would say that this graph, I'm sorry if I'm being mean, but it provides no information above and beyond what I could easily provide in a table. And we know that the kids understand the numbers already because they're able to do this. Now, again, it might be necessary at the beginning, but I would caution against this. At least at the very least, have it go from highest to lowest so they can see the trend or something like that, and they can talk about, I see, it doesn't make any sense. Why are trains more common than fire engines? But maybe in that classroom they are. But the point is, we want to see patterns. Another really interesting example that I keep thinking about is these are Cuisenaire rods. Anybody use them in their early math days? Oh, I have here a book using the Cuisenaire rods. I'm thinking if I could take it out, but the whole shelf might collapse, so I'm not going to do it. But a very important part about the Cuisenaire rods is that they are relational. They all have the same, so you're trying to say what blue, or how many blues, or how many yellows does it take to make a blue, or something like that. And you can see that you can start getting into fractions. So one of the things that's really impressive about these is they can go from very simple to very hard. Now, here's the question. Should you assign numbers to these sticks? And if so, when? Again, many teachers are tempted to say something like this. This is the longest one, the orange, so we're going to call that a 10. And this is the red, it's the shortest one, and we'll call it, I don't know, 1 or 2. And that works if children already understand the pattern of relations and how numbers relate to each other. But what these are supposed to be really good at is helping children both conceptually and in an embodied motoric fashion to see and think about and feel relations. So again, I'm not saying never assign numbers, but it's important in this case to assign multiple numbers and not to do it right away. Multiple numbers, like just for example, like if this is 1, it can also be 2. Well, what does that make this? That kind of thing. Okay. And I would also argue, I feel like I'm trashing all the favorite things. Dora the Explorer, I absolutely love, and I can still sing it from when my kids were young. So, despite what I'm about to say, I love Dora the Explorer. Okay. But what are they trying to teach about? Maps. And they say, I'm the map. And then they say, first we see the Ferris wheel, and then this, and then this. Well, that's good. And that's one way we can use a map. But think about it. If you were trying to tell somebody, would you draw them a map? It would be borderline insulting. Like if I say, I lost my keys, can you help me? And they say, I'll draw you a map. That almost feels pragmatically, something's going on. Why did you offer that? Just tell me where my keys are. I think I saw them in the living room on the table. And likewise, you just follow a path, and the first thing you'll see is the Ferris wheel and then the merry-go-round and whatever that is. You don't need a map for this. Now, there are situations where a map really helps. If I wouldn't to say, is this northwest or southeast or whatever? I know that's harder. But my point is that when we're teaching children about visual representations, it's very, very tempting to focus on objects. Good, but objects are important. But remember that they're not the end. That we're doing that in the service of relations. And so likewise, when we're thinking about multiple representations in chemistry, it's a really interesting question about, so I think this is a Fisher. Somebody shot out, I don't know the names of these, but they are ways of representing molecules that include important 3-dimensional information in traditional 2-dimensional ways. So you can draw this on the chalkboard, and it's been around and it's worked. And the chemistry professors internalize this. This is part of their knowledge now. And so they almost don't have to visualize unless it's a very complex molecule. They will know the structure of many common organic compounds just from studying and working with them. But the students, have almost none of that. And so again, how we get away, this is all great. If you want to emphasize how they bond, this can be really useful. But at some point, they do still, I don't know, unless we're abandoning it, still have to understand this, and then ultimately this. But then sometimes we can go too far when we get this and we forget about this. So, we need both. Now, this is a study by Lindsay Richland, where she compared mathematics teachers in Japan and the United States. And one thing that is interesting when you go into a Japanese classroom, you may be surprised that the teacher may cover only a few lessons in a few concepts in a lesson. American classrooms often have, particularly with so many standards that they have to meet, lots and lots and lots of individual problems. The question is the student getting the relational information? So the teacher would draw both and point out the similarities. That initial object comparison is critical to seeing the relational information, but don't end there. So it's kind of a balancing act. So one very simple sort of measure of this is that the Japanese teachers much more often drew and compared two similar but different problems. I'm not exactly sure what's going on, how different this is. Doesn't look very different. Okay, now let me see. I've got what, maybe 15 minutes?
Yes. Okay.
So I've laid the theoretical foundation. I think that's the most important thing, and probably spent more time, but I'm not gonna rather than rush through this, I'm going to just give you some important examples and maybe come back someday. So one of the things I've been interested in since graduate school which is now a very long time ago, is learning about relations through maps. So my very first study that became a master's thesis was about children learning the layout, and the layout, not just the route, in a simple playhouse, and then having to point when you're in one room, can you point to another one? Because that's what I said, what maps do. And we can think of a map as kind of like an analogy. Maps are not just copies of the world. No map is a perfect copy of the world because traditionally it's a piece of paper, and it's flat, and the world isn't flat. I know there are globes and stuff, but how you make these choices of what to represent and what not to represent is in some ways the whole science or art of cartography. So it's not simple, but I do think that maps can help us think about relations and patterns. So this is an example of what I mean. If I asked you how to get from, okay, help me out, Jackson to, oh my goodness, Mobile? Well, that's in a different state, sorry. Gulfport, there we go. You don't really need a map for that. I don't know what the interstate highway is, and it's not shown here because I don't need it. You would just tell me what highway to take. If there's a turn, you would say, when you get to so-and-so, turn right or left. It's pretty easy. If I want to say, do some sort of analysis of voting patterns, where do Democrat and Republican voters come from? A pattern might emerge, but then you would notice, okay, so some seem more concentrated in urban areas versus rural areas. That kind of thing, a map really holds a distinct advantage. So think about what it is you're trying to represent and what tool can do that most effectively. One very famous example of this, I'm sure most of you are familiar with it, but it's so elegant I can't resist. So this is John Snow's map to solve the source of the cholera epidemic in London about the same time as the American Civil War. I don't remember exactly. So what makes this so insightful, it's like the first geographic information system. He mapped individual cases, and see, a pattern starts to emerge. So it's very dense around here. It spreads out, but then there are some densities around certain neighborhoods where it turns out people are sharing water. And most of the water that was creating this problem turned out to be the Broad Street pump. And so he mapped the locations of the cases, and then he mapped the locations of the pumps. Now it becomes pretty obvious that the Broad Street pump here is the problem, and that this one might be contaminated, but much more likely is these people are carrying water to their homes and sharing it with others. So, it's going to diffuse like that after an initial concentration. So this is like a geographic information system. We have different kinds of data, and we want to represent it. We can turn layers on and off to see patterns. This is what I mean. This is what maps are really good for. And since the late 60s, there have been technologies for taking advantage of this. Drawing maps by hand is fun, but it's very slow, and it may be useful in some cases. But if you're trying to quickly solve like an epidemic, you need to be able to make different maps very quickly. And that's what Geographic Information Systems, or GIS, does. So I met Bob Colbert, I think in 2006. He's now Dean of Engineering and Integrated Science at James Madison University in Virginia. And he, long before me and long before most people, realized the importance of GIS as an educational tool. His PhD was in astronomy, and he had learned about this from studying remote sensing and trying to make inferences about what's on other planets and things like that. But he brought it home to Earth and realized that this had strong potential in education. So GIS stands for Geographic Information Systems. It's important that we distinguish this from what comes on almost everybody's phone now, which is GPS, or Geographic Positional Systems. that one letter difference makes a huge difference. In fact, in terms of your brain, you can think of it very simply as this: GPS bad, GIS good, because GPS has been shown, people who rely more on GPS have smaller hippocampi and get lost more often. It's like one of these technologies that's making us lose some abilities. Now, that's always been true. Like probably our handwriting got worse after the printing press was invented, but there's always trade-offs. But it's interesting to see, like, we're distributing navigation onto a machine now. Okay, I don't have a problem with that, but it does have cognitive and neural effects. So what makes GIS so unique is it's a combination of data and representation of data. So say, okay, the typical example, now very dated, is where would you put the next Starbucks? We're inundated with Starbucks, so please nobody do that. But if you were doing that, you would have to think about many things. You might want to think about street traffic, pedestrian traffic, car traffic, parking space, proximity to train stations, all of that, to make a best guess. And those of you who've done real estate or marketing know that these decisions are not easy and often fail. New businesses, not Starbucks so much, although they do fail, but starting a new business is a very, very risky venture, which frankly doesn't usually work out, but can lead to other things that do work out. So you really want to think ahead. Where will my customers come from? What is my business model? How do I get people, if I need to get them into a retail shop, how do I get them? How far will they walk from a parking space? You know, how often does the bus have to come to actually make it effective for people coming into my store? So all that kind of information could involve multiple different kinds of information. Almost all cities in the United States, it varies greatly because it's a hodgepodge. It's completely voluntary as far as I know. There has been some sort of convergence towards a standard format, but we're nowhere near that. But the good news is that almost all cities have data that you can project. So I teach a class on sort of thinking through geographic information systems. A lot of the students are interested in health disparities or food access, and that kind of data can be projected, and they just immediately see, like, there's this whole area of Chicago, the whole sort of southwest of Chicago doesn't have any hospitals, where there's, you know, a huge concentration downtown and then going north. So they can see that right away. Pops out. So these are the kind of, so I've got like maybe 5 minutes, less than that. I want to leave time.
Yeah, and I'd like to leave some time for some questions too, David. So
okay. Well, we've been studying how people solve complex problems and using GIS, and we think it's helping both their cognition and even changing their brain. So we're getting more. It's actually interesting that some of this is less activation after they take the GIS course, because problems that could be solved spatially or not spatially are more likely to be solved spatially. So they recruit that. And I'm working in career and technical education. Sorry, I ran out of time, spent too much time at the beginning, but I'll end there. And if I can figure out how to, there I am, I'm back. So I would now entertain questions. Oh, Robert Bateman. Wow. I haven't seen you in a long time.
Hey, David. Good to see you.
Hi, good to see you. Yeah, it's great to see you. He was one of the first people that got me into organic chemistry and realizing how hard it is. I still use the example of the Richardsons solving these problems together and all the multiple sources of information, ranging from gestures, computer simulations, previous publications, all of it, all together at the same time. Sorry, it's just great to see you. I'm done, sorry.
No, David, this is fantastic. And I love the way you weave together so many areas of human development, of STEM areas, of content, of just history. So thank you, it was just fantastic.
Yes.
I'm curious if people please want to put any questions in the chat or just shout out.
How do I get
it would
to
be
the
great.
chat? I don't see the chat. It's empty, that's why.
If I may, it's not a question, but a suggestion. Thank you very much, David, for the interesting topic. I work in the GIS world, and due to the importance of the ocean now, the hydrographic part is called the hydrospatial data rather than geospatial. So I would be very interested in spending more time in your last part of the lecture. So if you can come back at some stage.
I mean, I actually could do that. Yeah, I basically had 2 talks. Sorry, but you're absolutely right. And trying to work with some people at the Gulf of Maine Research Institute Concord Consortium to look. I mean, it's not just space; it's also time, and time becomes critically important to understanding climate change. And you know, on the one hand, geological time is slow, but on the other hand, you're trying to convince people of an immediate, urgent problem. And so it's kind of like you spent, you know, several years teaching them that these things take millions of years, and now you're saying we got to do something within 5 years. It's a little hard, I think.
Yeah, I had a problem last semester trying to teach people about the detection of objects using sonars, and I was struggling because I wanted them to see geometrically how the distribution of the sound goes and the shades and etc. And most of my students fail to answer properly the questions on the geometry of the propagation.
Maybe, I know it's a different geometry, but you could ask them, how does a cell phone, not the GPS, but the cell towers, how is it that we can make a call from almost anywhere in the country now? And it's this triangulation against cell towers. So that might work. Oh yeah, there's a great movie where the guy is on the Navy boat and he detects, it says fish in the water, which means there's a torpedo, and it's coming at them at like 50 miles an hour, and they're trying. But his expertise, you know, the slight differences in sound is really cool. I love watching experts in any field, you know, shoemaking or whatever it might be, because it just, you know, the 10,000 hours of practice that they've gone through makes them so distinctly different from you and I, that it's just fun to watch and think about what they're doing.
So if I may, Julie, I think we could invite David again for touching more on the GIS part and eventually GPS. And I think I would like to explore more on the...
Yeah, and maybe if we're done with variants, cross your fingers, I could actually come in person. I'd love to do that. I will
share my friend. David is fantastic. I would be happy to put you two in touch. You know, one thing, David, you were talking about that just reminded me, I don't know, just for other speakers too. I read a book years ago. It's called The 5 Faces of Genius. And it really talks about how people come up with new ideas. And I think you and I are probably very much alchemists, because we kind of blend and connect a lot of places. And then it got me thinking about our own spatial awareness and even how we connect things academically. And anyway, I'll put a link in the chat just because it's a really
I don't know if I want to be. I very much agree with the alchemist, although alchemy didn't really go anywhere. So.
Well, there's that.
Yeah. Well, I've been recently trying to learn the guitar after having studied clarinet and piano, and there's a negative transfer of relational patterns. Like, for example, in guitar, you have only 4 fingers, you know, and it's like, you know, in piano, you use your thumb all the time. So it's really next to impossible to get over that. But eventually it starts to help, but I'm far from that.
And I wonder how much of that is fine motor skill development too, and when that happens, and when we start to lose that over time.
Oh, thanks for that too, alchemy. But you can help. It helps to try something new.
Yeah, I just have to build back, you know, like all of this, like what Julie was starting to say. So my bachelor's is in geology, but David, you know, I'm in STEM education now, right? And so I'm thinking about systems, relationships, about the education system, but I have always, and so it's really helpful to see your program, even in grad school, always immediately interpreted the information I was learning about education systems, dynamics among teachers, theoretical concepts, spatially in my head to align with my geologic background as an undergrad, to say, oh, if I can think through the structural challenges that we confront in geology, but from the lens of education, that is how I view the landscape of education and my interactions within that. So like the fact that you started your talk there is really blowing my mind, because that's how I've been ever since. Like even when I read a text, like that's how I think spatially about the information in the text, or theoretical construct.
When I hear a person talk like this, I got into this because I'm horrible at it. And this goes back to 1913, Adler's overcompensation hypothesis. We study what we're bad at. And when you describe that richness, it's sort of like a food that you never tasted before. Like I can appreciate that you enjoy this and you can do it this way, but I can't really experience it. I really honestly don't have that feeling. I can look at something that helps, but in my own head, no.
But you've done it, like the way that you've described it helps me articulate like exactly like how I'm visual. Like I was telling Julie actually just the other day when we were moving furniture in the center, I said I want to say it's like Jacques Derrida or somebody, I can't remember the exact philosopher's name, but there's a saying in philosophy that talks about your mental furniture. How do you organ, right? And so I think that's kind of like related to here. I told Julie, I said, I appreciate how much you care about the rearrangement of furniture, because that's also like mentally how I'm thinking about my work in education. And so this is just like your presentation, I feel like is giving more language to characterize, and think about like 2-year-old daughter through this.
Yeah. And there are now a couple of online games that you can play that are actually really useful, both as tests and as training. I can send the links of, we're getting better now at gamifying this stuff so that, you go from struggling to recruit 40 people to your research to having over 1 million if you make it fun. So I haven't done that. Mine's still 40 at a time. But there's a lot that can be done. I got distracted. Can't find Zoom. There you are. Okay, but I wish I had your abilities. I respect it is basically what I can say, but I don't understand. I don't feel it.
Which kind of circles back to that original chart you showed us at the beginning about verbal and math abilities and sort of where people end up.
Well, I was a psychology major. I did, and I was going to be a doctor, and much to my mother's chagrin, I chose psychology. And she always pointed out, almost the day she died, that I could have been a doctor. But
you're a real doctor.
Yes, I can't help you if you're sick. My daughter's a doctor, so there. Yeah,
well, thank you so much for your time.
I'd love to come back, and I'm sorry it was so rushed.
We would love to have you back.
Send me emails.
And thank you all for joining us.
I loved it.
Really appreciate it.
Take care. Bye.
Thank you all.
Thank you. Bye-bye.
Bye.